Much better. Thank you. Hello all. Thank you for coming here. Thank you also, Stephanie, for giving this talk to us. I would also like to thank the sponsor of the room, which is Q, an IT and digital talent firm in LA focused on finding local technology talent in SoCal. If you're interested, please contact them through their website, qconnects.com, or feel free to talk to them if you see them around. So today, now we're going to have a talk by Stephanie Lockwood-Childs. She's president of her local LAG Linux user group in Santa Barbara, and she's also the president of her own company, VCT Technologies. She's going to talk about two build systems, Buildroot and OpenEmbedded. The embedded Linux ecosystem offers a healthy diversity of build systems tailored to different niches, unlike proprietary OSs that tend to present a build system controlled by the owner as the one true build system. This presentation will focus on two of the embedded Linux build systems that have exhibited the most staying power, Buildroot and OpenEmbedded. I would also like to remind you after the talk to please fill out the survey and the feedback form for this particular session and our presenter. Thank you.
Okay, here we go, starting with the title screen, which sometimes is kind of filler, but in this case I think serves the vital purpose of letting people figure out if they're actually in the right room as they trickle in after the intro. And actually, there is another room that you might have intended to be in, since there's two embedded talks right now. And if you get up and go to the other one right now, I won't hold it against you. It's actually being done by my coworker. So, yes? Now? How about now? Okay. Okay, so today we are going to talk about these two wonderful build systems called Buildroot and OpenEmbedded. It is not aimed at people who are experts in both of them. If you're already an expert in both of them, you'll probably find it to be rather a review. But if you know at most one of them and you're curious about the other, then I hope you'll find something useful in this talk. So we're going to start out with the burning questions that I posted in my abstract, just so there's truth in advertising and all. Let's look at the question, between Buildroot and OpenEmbedded, which build system has the smaller learning curve? Which build system is the foundation for many consumer electronics distros? Which build system is the more natural choice for MMU-less micros? Which build system has its own theme song? Okay, well, motivation. So now we move on to the high-level comparison. I found these wonderful pictures that show how at least I tend to think of the two build systems. Buildroot is my X-Acto knife, and OpenEmbedded is my beloved Swiss Army knife. So that should give you the hint that one of them is super useful but simple, the other is super useful and featureful. So we'll start out with the section on Buildroot. This one is small and simple. Let's look with its past. Once upon a time, it was started by a guy named Eric Anderson in 2001 as just a set of makefiles for building a ulibc-based rootfs. How many people already know what ulibc is? Okay, Not 100%. So I will clarify that it's supposed to be UC-libc. Oh, typo. Did I do it again? Okay, just once. Phew. All right. Yeah, it's nobody should have raised their hands. Yeah, that was just to see if you're on your toes, man. Okay. So, UC-libc. UC-libc is a tiny little libc that's been around for a long time, way longer than this bionic stuff that Google invented. And it was intended for embedded systems, including ones that are so small that they don't even come with an MMU. Do I need to explain MMUs in like a couple sentences, or everybody know? Do it? Okay. So the MMU is the fun thing that allows your user space programs to not stomp over each other in memory. So that's why MMUs are a lovely thing to have if you can spare the silicon. But when you're going super small, super cheap, you don't always get the MMU. So UC-libc was worked on by was started by this guy, Eric Anderson. And he just came up with a build system to go with it. Later on, glibc was added as an alternative, which is a very convenient alternative since many embedded products do have MMUs, and they keep getting more and more resources, so the tininess of being able to compile out little bits of your libc is not so important. But UC-libc is still supported as an option to this day. Buildroot is still, after 14 years, is still a highly active project with over 5,000 commits by 183 different contributors during 2014. And a little footnote, I got those stats from openhub.net, which is the Black Duck's renaming of that service. Used to be called OLO, maybe because they had no clue what OLO was supposed to stand for, and they got tired of people asking about it. But anyways, fun stats. And as an example of the type of project that might be using Buildroot, Analog Digital actually does their official vendor support for Linux on Blackfin. And the Blackfin is actually an example of one of those MMU-less processors. They have something that's kind of gives you some memory protection, but it's not a full MMU, so I'm going to say it's MMU-less. And it's a really neat processor for some things. It has this powerful DSP stuff in it, but it's not exactly your average embedded CPU. So let's take a look at how the Buildroot developers describe their system. Buildroot strives to make it easy to generate a root file system, hence the name, Buildroot. This is what we want to make Buildroot good at, building root file systems. So, that was hard. In my words, if you can build a kernel, you can build a Buildroot image. That's how simple it is. So, once you've got the kernel part down, it does not take you much longer to get the rootfs part down. So let's take a look at the host side tools that you want to have if you're going to be doing Buildroot builds. There's a couple classes of these. There's the pre-installed ones that are dependencies that you are responsible for getting on your host system, which includes the normal host tool chain, just for building stuff for your own dev system. Optionally, you can provide your own cross-compile tool chain, but this is not mandatory because Buildroot can do it for you. There are instances, though, where the vendor likes a particular tool chain and they recommend it, and then you might want to use one of those external. Like, for instance, I think the Blackfin might do this. so that to make sure that the fancy linking that needs to be done without the MMU gets done properly. And you need more, basically, what I would consider build essentials, things like make, patch, sed, Perl, Python, and it mostly uses wget for source code fetching, although there could be particular packages where you're going to want to have one of the source code control, Git or SVN to be able to pull that. So there's the other category of tools that go on your host, which is Buildroot provided, and that is everything else, pretty much. All the ones that are not those classes, including the cross-compile if you dare to use the one that's built by Buildroot. So this is not the full directory layout, because this is not a whole tutorial on just Buildroot. This is what I consider highlights from the Buildroot directory layout. We'll start with the top-level makefile, because this build system is controlled entirely by your old friend, make. Doggone it. Hit the wrong key. Then we have a .config, which kind of carries the kernel building theme that I already mentioned. This is the config file for your rootfs itself. Then you have a directory that has skeleton files. Does everybody know what I mean by skeleton files in the context of an embedded system? It's for the embedded system, you will have applications and stuff, but stuff that needs to get built by your build system, and then you'll have a few random files that are convenient to just kind of stick in there. They're text files. They don't need anything done to them. So it's a common practice to go ahead and overlay the contents of a skeleton directory, and they'll be laid out kind of the same way that will appear in your eventual image. So, like if you're trying to cheat and stuff in a few etc files, they would be under skeleton etc and so forth. Then we have the packages area. $package is my placeholder, meaning whatever package you are currently interested in. Like, say it's netcat or whatever. That's going to have its own subdirectory named after the package. And under that subdirectory, it has two mandatory files. One is a config.in, which happens to, again, look a lot reminiscent of those kernel config.ins, because they basically lifted the exact same syntax. Then you have a .mk file, which is just the make file, which is going to control the build of your package. Then optionally, you could have one or more patches, because you start out with an upstream tarball that's fetched from someplace that might not even care about embedded, right? They might have all kinds of goofy, uncross-compile friendly stuff in their package, and at first you would have to make a patch to fix it, and then ideally you could submit it upstream, but in the real world they don't always get accepted. Some maintainers don't care. Some packages don't really have active maintainers anymore. So sometimes the embedded guys have to carry around a handful of patches. Now you've got the .hash file, and this is again optional, and in fact not all of the packages that's provided in the official Buildroot tree even has the .hash file, but it's a good idea. What it is it's checksums for that upstream tarball that you download to know that you downloaded an accurate version. Like if you go to a web page and you're downloading a tarball yourself, a lot of times they will put on, and this is what the checksum ought to be when you've downloaded a good version. Then there's another really important directory called output, and under here you have the host subdirectory, which has all those fun generated host tools that I told you that it could build for you outside of the core initial set. And then you'll have the build directory, which is the working area. For every package that you're putting into your rootfs, you're going to have a subdirectory where the actual work is done. It gets unpacked and compiled in there. Then you have staging. Staging is a kind of a common concept among the embedded build systems specifically. It's the if you think about you're building something for your own host system, then it's welcome to go find the libraries under user lib most of the time and the header files under user include. But if you're trying to build for a totally different system, you can get into all kinds of messes by letting it find your host's header files instead. It could be totally different versions. Never mind, the libraries will never link against your, your ARM stuff if you're building it on an x86. So what happens is they generally make the staging area where you put in all the target specific headers and libraries. And then when you're building the packages, you force them to look over there. Say, don't link against stuff in user lib. Link over there in the staging. And the target. This is probably, it's like the RPM Buildroot for those of you who build packages natively. It's the place where you install everything that's going to end up in your file system. Again, you can't let the packages do their default of trying to stuff things into /user local, right? You're trying to collect them all over here in this place that is segregated for target binaries and libraries. And finally, you have the images directory, which is the end result. When you've done your Buildroot build, the images pop out here. These are the files that you would actually install to get your new Buildroot rootfs up and running. So let's take a look first at an example top-level config. That was the dot config over here. This is highly truncated, just the top of the file, but you get the general idea. This is should be a familiar looking config style if you are used to compiling your own kernels, because they did steal the config format. All they did was where you have config underscore blah, they turned it into these br2 underscore blah. Other than that, it's exactly the same. You can do, well, okay, you don't really have equal m's here. But other than that, equal y for things that are turned on, and blah, blah, blah is not set with the pound sign for stuff that's disabled. Now let's look at an example MK file for a specific package. This is the kind of thing that this is another thing that you might actually want to create for yourself when you start doing Buildroot. If you want to pull in your own nifty custom package. This example actually comes from the Buildroot manual, and in this case, it is not truncated. This is the whole thing, fits on one page. Pretty nice, huh? This is a makefile syntax, but they have some fancy stuff that allows you to be really brief and just basically set variables, kind of metadata variables, if you're doing one of the common types of packages. This one shows an AutoTools build system package. That's one of the supported types, but you also get CMake and Python-based packages, things that use set of tools or dist tools. There was one other was a little more obscure. I think it was Lua. But anyways, that covers a fairly large number of useful packages out there, especially between those first three I mentioned, AutoTools and CMake and the Python build system. And if you look at the ones that are a little more manual, they're still not that bad as long as you're familiar with makefiles. It's the Buildroot manual actually is great documentation, and you can go in there and know what targets you need to implement and which variables you need to set. If you're doing it from scratch for something that just has a plain makefile or even some other unsupported build system like that, what's that Qt one called? Anyways, so now let's take a look at the high-level workflow. If you're working on a Buildroot project, you'll have the initial build, and then you'll have subsequent updates. For your initial build, you're going to start out with a make menu config make. That looks pretty similar to the kernel. Your next step is to go install the images on the target, and that part is up to you. You have to figure out what's appropriate for your board. But then again, the kernel build system doesn't tell you how to use Lilo or Grub2 or whatever. So that part is up to you. If you're doing an update, you go in there and make your changes. You might be changing the configs. You might be changing packages, adding them, or adding new patches. Or you might be stuffing in more odds and ends little files with your skeleton. This time, the recommended thing for beginners at least is to do a make clean before the make. And this is because Buildroot actually skimped a little when it comes to keeping track of things. The kernel, that's one of the nice things about the kernel. If you do weird things, change your flags, change your architecture, it'll notice this, and the next time you type make, it'll go back and start things from scratch like it needs to. But Buildroot decided to be a little simpler, and it leaves it up to the user to know when it should make clean. So the safest thing, until you're sure you know what you're doing, is to just always make clean, right? Luckily, Buildroot builds don't tend to take a huge amount of time, so that's usually not too onerous a procedure. And then, poof, you have your stuff pop out in the images subdirectory, and you go install images on the target. So basically, it's a pretty simple workflow. Not much complication added by the build system. All the complication is generally in if you're trying to get a package that used to be run natively and the transition to making it cross-compile, but I don't know of any build system that's really going to help you with that. Okay, so now we're switching over to the other half. This is the OpenEmbedded side of the story. OpenEmbedded has always been, from almost the very start, a distro collaboration. collaboration between people who are working on embedded distros. Back in 2003, started with developers on the OpenZARS team, but it quickly got adopted by a bunch of other embedded groups. One of the first ones was Familiar Linux. Those were the ones who were doing the IPACs once upon a time, Linux running PDAs. And Gumsticks was actually a vendor that jumped on the bandwagon pretty early. And one of particular interest to me is the WebOS team over at Palm back before things got unhappy and they stopped making phones. The WebOS team got hold of this OpenEmbedded stuff, which I have retroactively labeled as Classic OE. We'll find out in just a moment why I did that. It's because after OpenEmbedded partnered with the Yocto project in 2011, they started a whole new fork where they implemented some nifty new features that and named the new stuff as OE Core. So Classic OE is basically the pre-2011 stuff, and since 2011 it's been going along with OE Core, and it has more nifty features. And if you're starting a new project now, you would definitely pick OE Core. So examples of distros that are now using the modern OE Core as their basis, aside from Yocto, which I mentioned in the previous bullet, include Angstrom, SHR, OpenWebOS, and LunaOS. I bet most of you have not heard of the majority of those distros, but there is a strong community of enthusiasts hacking away at each of those. And it's not just the enthusiasts that have been happily hacking away at OE Core. A lot of the changes that ended up being made at the request of the Yocto guys were actually aimed at getting it more friendly for use by vendors who have their board support packages. And nowadays, there's a large list of vendors that base their board support packages, BSPs, on OE Core. That would be starting with Intel, one of the ones who started the thing, but also AMD, TI, FreeScale, Gumsticks upgraded from their classic OE to the modern OE Core. And there's actually a bunch of others if you go looking on the website. So let's hear what the developers say to characterize their own build system. It allows developers to create a complete Linux distribution for embedded systems. Some open embedded advantages include support for many hardware architectures, tools for speeding up the process of recreating the base after changes have been made, and it can cross-compile thousands of packages. This is all from their wiki. This is not exactly, we build rootfs's and that's what we do and we do it well. We support distributions, which does involve more than just cranking out a one-time rootfs. So here's my summary. If you can do it with embedded Linux, you can use OpenEmbedded to do it. So let's look at the tools situation for the host computer again. Again, you need some that are pre-installed. The exact list actually varies by the specific distro that you're using But here's an example from the SHR Wiki. It's mostly stuff that you would find in Build Essentials on a typical Ubuntu. You might have to pull in one or two others. You can also find some convenient install commands that if you're doing Yocto, their guide mentions you can apt-get if you're over here, or you can yum install this if you're over there. They don't actually mention what you can emerge yet, so. So you also need the actual core critical build tool that OE uses is not in this list of stuff that you get from your distribution. It is a new one called BitBake. This is not Make. This is a nifty Python application that has very different syntax and has a lot more features. We're talking Swiss Army knife here, remember? So once you have BitBake and the miscellaneous host build prerequisites, then OE manages to build everything else. So there's a fair amount of other things where you'll get blah blah - native, and it's just compiling it for your host use. So for comparison, we're going to take a high-level look at the directory layout. And this is actually harder because OpenEmbedded is so flexible that it gives you flexibility in how you lay out even your top-level directories. So different distributions can do it differently. So I have these general tags for meaning wherever your distribution decides to put it, check your distro-specific docs. So one of the important areas is your project-wide conf area. That'll be a directory somewhere. And it has two critical files in it. The first is called local.conf, and this has global build options. It's a great way to control things that apply across your whole build. And you have your bblayers.conf, which is a list of layers. Now I know that's another case of computer people co-opting words that already have meanings, so maybe I'll take a little time now to explain what they mean by layers. You have a group of packages which is being maintained by some set of people, and it's this collection of packages that are built for the OpenEmbedded system. Then the collection as a whole is called a layer. So you can have layers that have different purposes. Some of your layers are going to be board support packages. Like this layer has stuff. If you want to be building, on embedded Intel boards, this one has stuff if you want to be building on Freescale ARM boards. Or they can be kind of theme dependent, like these guys over here are maintaining something that has Qt support. You can add Qt to your embedded system. But in each case, they call those a layer. So there's a ton of them available, and you need to decide which ones you're going to use, and then you need to tell your BitBake which ones it needs to find and include in your builds. So that's what bblayers.conf is all about. So now you have the OpenEmbedded-core meta, and that is actually a layer in itself. It's got all kinds of really base, important stuff that the OpenEmbedded team maintains themselves. I'm going to point out just a few really interesting things from there. Namely, under the conf directory has lots of important config files that you probably won't have to change. So I'm not putting them up here. But there's one that's really useful. It's called confdocumentation.conf. I wish every layer would provide a nice documentation, but OpenEmbedded did provide some helpful stuff. This is like a glossary for the of keywords for stuff that apply to the OpenEmbedded. Next, you'll have a directory called classes with a whole bunch of files called blah blah.bbclass, and these are how BitBake gets to be so flexible. These are extensions for BitBake. It will dynamically load up the BB classes for all the layers that you have enabled and learn new tricks. Like, for instance, there's a BB class that teaches BitBake how to crank out the right SD card image to just plop verbatim onto your Raspberry Pi. Now, that's not the kind of thing that you would normally put into, an upstream build tool. You can't imagine Make knowing about SD card layouts for Raspberry Pis, right? But because it has this extension mechanism, the people who are maintaining the Raspberry Pi stuff can throw that in there as a BB class. And then you have, this is actually a set of directories, recipes-blah. In some layers it might be just one directory called recipes, but if you have a big layer, then it's often useful to have a little more organization, like recipes-development, recipes-whatever. And inside each of those recipes directories, those are the core files that describe all of the packages that it knows how to build. So you'll have more subdirectories under the recipes, like you'll have recipes/glib. This tells how to build the glib library. And under that directory, you will normally have one or more BB files, which stands for BitBake format. You'll frequently have .inc files, which are for including in BitBake files. And then you need a place for patches too, because again, just like with Buildroot, there's the common problem of your upstreams not always being very cross-compile friendly. So sometimes you have to carry around those patches that make it compile with the cross-compiler, or even just for a specific architecture. Like maybe they've got big Indian bugs in it, and you're actually building for some big Indian board, although those are pretty rare nowadays. So the patches don't actually go even in the top-level directory of your package, they have where the BB files, they could go in multiple places. There's a file subdirectory you could put them in, and that means that any of the recipes in this area can get those patches, or you can actually have multiple versions of a patch. Say glib 1.2.3 needs that patch, and so if you're building that one, you need the patch. But then I also know how to build glib 1.2.20, and they finally fixed it upstream, so I don't want that patch anymore. In fact, it won't even apply. So you can actually sort your packages according to the generality. Did I mention this was a Swiss Army knife? Now we have the build area. The build area is, I've only shown 3 bits of it, which is somewhat misleading. Makes it look like it's nice and simple like the Buildroot one, but that is actually a false impression because these are only top-level directories where you can have a bunch of other subdirectories. In particular, sysroots, you have the the generated tools, headers, and libraries all fall under the sysroots area, but you'll have different places under sysroots for the things that are your cross-compiled libraries and headers, and for things that are your native tools that are your bonuses for to add to the host tools that you installed with your package manager. And you can actually have multiple different targets living in the sysroots, because say one day, say you're maintaining some fun stuff that runs on multiple embedded boards. Say even one of them is an ARM and one of them PowerPC. You can have sysroots that are keeping track of the PowerPC libraries and headers and the ARM libraries and headers in parallel. And that same architecture specific areas also goes for the work area. You have package build directories, but it's sorted into multiple subdirectories. And in fact, in this case, you could have, if you know about on RPMs, how sometimes there's the no arch, right? This is stuff that goes for regardless of architecture. You'll have a no arch area for work, which are things that you could use between your PowerPCs and your ARMs. And you'll have the host system area in work, which has the stuff that you built for your tools. Then you'll have the ARM, and then you'll have the specific flavor of ARM, the one that goes for your actual platform you're building with, because two different ARMs could be using two different kernels, and they need to link against different eras of kernel headers. So, really convenient if you need those fancy features, like say you're maintaining a whole host of different boards for your company or whatever. And then we have the deploy area, which is basically the equivalent to the images subdirectory over on the Buildroot side, except it has more. In addition to the full images that you would just plop onto your embedded target, it also has binary packages that can be installed individually. This leads us, well, not quite yet. I'll talk about it a little later with the workflow. Now let's take a look at some specific examples of OpenEmbedded stuff. This is specifically taken from Yocto, a Yocto build that I did for a little Raspberry Pi project. And this is one of the simpler, shorter local.confs. They can get way longer than this. In fact, the default ones are way longer, but they're mostly comments, so don't be too alarmed. This I have distilled down just the essential stuff. Like, for instance, how many parallel processes do I want to be using while I'm building stuff? Well, I've got a beefy old 8, it's an Intel with 8 cores, so the recommendation is that you kick off a couple of threads per core, and I tell both BitBake to feel free to spawn up to 16 processes in parallel, and then when there's a make that's building a particular package, it is also free to spawn up to 16. This one right here, this inherit RM work, this is basically a space saver on your development machine. Some people like to enable this. If you have just oodles of storage and you don't care about using it for builds, you would probably want to leave this out because it's kind of convenient to be able to go back and see the work that was done in all your builds. The machine selection, this is pretty key. You have to tell it which of the supported machines you're building for. You can, however, do it as an environment variable. You could just pass it machine equals when you kick off the bitbake. But that is why this is a question mark equals in make syntax. That means if you haven't said anything else, anything to the contrary, then go ahead and pick Raspberry Pi. And then we have a distribution selection, which is normally okay to set it just with the normal equals because you're not usually switching between multiple distros in the same build area. For one thing, they can have different directory layouts, like I said. And the final important one is you're picking what kind of binary packages are going to pop out when you're done with your builds. It actually has 3 choices that I know of. One is IPKs, .deb files like Debian, or RPMs. And IPK is basically the stripped down embedded version inspired by .deb files. So I tend to prefer that when I'm building for embedded platforms. So now here's a look at sample bblayers.conf for the same little Raspberry Pi project, in fact. And you can see that there's these 2 layers are from the distro. These are maintained by Yocto. This one is for my specific board. And this one is the generic OpenEmbedded, which just has a ton of useful packages. They're commonly used. Okay, now let's look at an example recipe. This is equivalent to the .mk file that we looked at earlier. And I decided to make a libfoo recipe that does the equivalent of the earlier mk file, assuming that libfoo still uses autotools. And it just so happens that this is not a truncated file. Again, it fits into a nice little 1 page. And this is because they made the common case nice and convenient as well. It's got a little different metadata. For instance, in the Buildroot, remember how it was optional to specify your checkzones for your downloaded files? Well, in OE Core, they decided that it was not a good idea to have it be optional. They started making it, asking you to put it in all the recipes, basically. Here we have this little S where it's defined as various built-in variables that you kind of have to learn if you're going to start writing recipes of your own. This workdir stands for wherever bitbake decided to unpack your package, which it depends on how generic it is where it ends up. PN stands for package name, PV stands for package version. And these things are actually inferred by bitbake based on how you name your recipe. That's a little fun trick that they actually took from the Gentoo eBuilds, I think. So suppose this file was saved to libfoo underscore 2.3.bb, then it would say, okay, pn is libfoo and pv is 2.3. Some packages, a lot of packages use that convention, but it's just a convention, and it can easily be broken. So you might have to specify something different for this S, which is how do I find the unpacked source. This line just says inherit auto tools. That says do all the normal things that you need to do for auto tools, and it's automatic from that point. Unless you need to do something special to, fix package-specific bugs, then this is all you need. So now let's take a look at an example workflow. This is actually just a kind of a sample because, again, OpenEmbedded is so featureful you may use it in many ways. So for your initial build, you always have to edit the config files. This is in place of running the make menu config stuff. Oh, come on, stop that. Okay, so you edit your config files, namely the local.conf and the bblayers.conf that we covered earlier. Then you pick an image, of which, of course, there is always multiple images that you could choose, depending on what fits your needs. You just say bitbake my image, whatever, it could be bitbake console image. All you need is a initial simple console build to start trying things out. Then you go install images on the target. Now sometimes this is more convenient than the Buildroot, depending on whether the people who are putting together your board support package, if they were ambitious or not. Like for instance the Raspberry Pi guys, you'll go find under your deploy area, under the images, you'll find a nice tidy little image file that you can just DD onto an SD card. Others, you have to figure out how to get your U-boot in place and then use your U-boot to get your kernel on. You might have to format an SD card and make up different partitions, completely dependent on what board you're trying to use. Say you have your initial build, and now you're in the mood to do updates. So there's actually a fork in the road now. You could go for the full image choice again, in which case you just run bitbake image name again. You don't have to go and do the clean if you're doing things properly. Like say you pull in say you do your git pull and you get a whole new fresh set of recipes that you've heard are going to do wonderful things and make all your bugs go away, right? So now you just go in there and go bitbake console image or whatever, and the new image pops out. You're not going to have to do the clean step and redo your whole build, which is a good thing because bitbake builds do tend to take a little longer than the Buildroot super simple stuff. So then you go install the images in Target, whatever the normal drill is. But the other choice is you can also build your nifty new stuff as individual packages. Like say, for instance, you started with the console build and then you decide, but I really wanted to use this one other tool. My console image is missing TCP dump and I miss it so much. So you go in and you bitbake TCP dump, and out pops a package under the package area, which you can then use SCP or whatever your wget, whatever your weapon of choice is to get it over to your target and install it with the package manager. Or you can use the package feeds, which means you have your packages exported basically for the apt-get. You have the Debian and Ubuntu maintains this web server that has all the metadata for the packages and the packages themselves arranged just so. So if you've set that up, say you're running a little Lighty or Apache or whatever over on your dev box, you just do bitbake package index, and that will refresh the metadata over in your feed area, And then you go over to your target and you do the equivalent of apt-get update, apt-get upgrade, or yum install, whatever, In fact, you could do, I guess you could do those, but I've only done this with the IPAC format, in which case you're using a different, slightly different package manager named OPackage, but the concept is totally the same. So then you would go pull the updates from the target as if you had your own little local apt repository. So we're going to go revisit those burning questions from the very beginning and from the abstract, and hopefully discover that we have gotten some illuminating answers. So between the Buildroot and OpenEmbedded, which build system has the smaller learning curve? From the audience. Buildroot. Which build system is the foundation for many consumer electronics distros? OpenEmbedded. And fewer. Consumer electronics? I can't think of many. Especially now. I mean, it used to be, but a lot of them migrated. Yeah. Which build system is the more natural choice for MMU-less micros? Buildroot. Which build system has its own theme song? You might need a little hint for this one. So, moment, please. OpenEmbedded. So here we go, burning questions, the sequel. This is your big chance to stump us all with fresh burning questions about Buildroot and or OE. It begins now. Any questions? Yeah. For the config for the OpenEmbedded? Yes. Yes. You would just use a local Git repository for the configs that you are interested in. You could totally use these for a tiny x86 system. In fact, the OpenEmbedded actually has as one of the default targets QEMU x86, where it runs inside a little QEMU VM. Yes, yes. So you would be doing things the OpenEmbedded way if you go with the vendor. That was one of many vendors that now use OpenEmbedded as their base build system. How would you compare both of these systems with using CrossDev and Gentoo? You actually asked the right person, because I actually have done that too. He knows, because I'm a former Gentoo dev. The Buildroot is, to me, the really quick way to get a new board up that doesn't already have an existing SDK that you actually want to use. So I would say that Buildroot is a quicker way for most people to get started with it. But if you're already a Gentoo person and you're wanting to do stuff, the main difference with that is that CrossDev didn't have the image creation stage really. I think that's the main difference. Now with OE, it's really way different because CrossDev doesn't give you all the well, it depends. If you want to install portage on all your little OpenEmbedded devices, then maybe you could probably do something similar. But a lot of the OpenEmbedded devices might be a little bit resource constrained for the wonderfulness that is portage. So the O package plus the iPack feeds, I think, is a good choice for those cases. Does that make sense? Okay. So if we're done now, I'd actually like to make a quick announcement which has nothing to do with my talk, except that you find people had the good taste to be here. You might also appreciate Munchkin the card game, because that is going to be happening downstairs in the game night. Me and my other half have brought a gigantic set of classic D&D Munchkin cards, and we're looking for people to come play with us. And the other little announcement is that SCaLE, if any of you people happen to be in the Santa Barbara area on a Thursday night, say you're an LA person who tends to drive along the coast, I would encourage you to get in touch with me. We would love to have visitors at our lug. So that's all.